guys saw, I did get it working after class. I went back and looked at a few things. So what I've got running here right now is the PID controller. And of course, we're looking at a trend right now. And you can see that it's ringing because, you know, it's just a really fast system. So when the set point changes, you get this ringing going on here, but then the system settles down and it just starts tracking. Now I hid the set point here for a little bit because I wanted you to see that ringing. Okay, but so you see the ringing there. Oops, I guess I didn't add it. Set point, add. All right, and so here's the set point. Okay, and you the cyan kind of color now is the set point. And you can see the red, which is the actual output, is going up there. Now, it didn't quite reach it because it's changing so quickly. So if I slow it down, so that it stays for a longer time, you should see that the red, which is my actual control, or the green is the actual control output, but the red is my actual process variable. And you can see over here it's still changing too fast. Okay. Give it about 30 seconds so it's got time to reach that final value. So again, the cyan color is the set point. And so we have this ringing happening here, but then it settles down and it just slowly drives the system so that right now it's supposed to be going to 750, so it's coming down, and then it jumps back. The set point changed on me again, so it still didn't reach that final value. Go for 40 seconds and should see. So it's up to 244 or 2,460, 470, 480. You can just see it climbing. All right, it's just taken forever to get up there. Okay, so we're at 2496, and then it changed on me again. Okay, so but you can see that it's coming here. So the steady state error is going to 0. So remember, that's what the integral piece is for, is to drive it to 0. Now, if we try to change some of these gains, we can maybe try to speed it up a little bit. That may increase ringing. Okay. All right, so it's you know, so it's moving here. So, you know, the ringing is still less than the amount of the set point. Okay. And, but notice like my values here, okay, so the WX1 is my proportional gain, WX2 is the integral gain, and WX3 is the derivative gain. All right, but that's before scaling. So these are all scaled. All right, so it's 2498, 2499. And then it changed. So you can see that the red came right on top of that. So you can see it's definitely tracking, but it's kind of a slow system here. All right. And if we turn off the control and go back to open loop, all right, just to kind of show you this toggling, right? So anytime if I'm in open loop, remember X4 was what turned on open loop. And when you're in open loop, you get all this ringing going on here. So we have all this ringing going on here with this open loop. Okay. But if we turn on the controller, Then we have just a little bit of ringing. Right up here, the ringing was going way beyond. I mean, I've got my scale at 3200 now, and the ringing was going way beyond that. But now there's just a little bit of ringing, but it's way below the set point. Okay, so it's bouncing around in there some, but way below the set point. Okay. All right, so let's take a look here at the logic. And so I basically have two rungs here doing the control, okay, which is what I had the other night, but I didn't quite have it complete the other night. So I have rung 7. Okay, let's see. Rung 7 is moving the set point value. Okay. And yeah, so those are just moving. So rung 9. Okay, so rung 9 is getting the previous error. So if you remember, we had to, we're calculating the area under the curve. So to get that, we had that, what I was talking about on Tuesday, 0.1 and 0.2. Well, in this case, the 0.2 is the error. So the first thing I got to do is move the error to a new value, which I called previous error. So I'm moving error to the previous error. Okay. And then I'm going to move the, or I'm going to calculate the new error, the set point minus that. Now this is only happening when the timer is done. So I've got that delta T timer running, and I'm only doing this when X2, which is just turning the controller on. So when the controller is on, but also it's only doing the calculation when the timer is done. Okay, now remember the timer's running at 5 milliseconds, so it's doing it pretty quickly, but it's only doing it one scan cycle that the timer is done. And then the next scan cycle, the timer's counting and it's not doing it. So it's only doing it, over here is my delta T accumulator. It's only doing it when the accumulator hits 5 milliseconds. That's the only time that this rung is doing anything. So it's moving error to the error previous, calculating the new error. It's just pretty much forcing delta T to be 5 milliseconds for the calculation down here. And then here I'm calculating what my integrator output is. Now this integrator output piece, this is the trapezoid. Okay, so this is calculating the area of the current trapezoid, which is the error plus the previous error, times delta T divided by 2. That's the equation of the trapezoid. Okay, so that is the error, or the area underneath the curve for that 1 delta T, and then I'm adding it to the previous value. So this is the integration piece. We have CO integrator is equal to the trapezoid plus what it was equal to before. So this is the part that's going to grow and grow and grow down here on this box. Okay. And then the next box is calculating my derivative piece. Okay. Now the derivative piece here is the slope, right? So that was like when we were doing scaling back in like week 5, we were doing scaling, and you had your y value, which is in this case is my errors. So it's error minus error previous, and this is a minus sign. This is a plus sign up here. This is a plus sign in this box, but this box is a negative sign. And then I'm dividing by my delta T. And just to be safe, I just put in a 1.0 here to just make sure that it was going to do the calculation as a floating point. I really shouldn't have had to do that, but it certainly doesn't hurt anything to do that. And then we go to rung 10, and now this is where I'm scaling. So when we look at the simulator, I have WX1, X2, and X3. Those are the gains, but those are just for me to adjust the gain, but what the actual gain is WX1 divided by 2000, WX2 divided by 2000, okay, to get me the gains for the proportional gain and for the integrator gain. And then the derivative gain, I'm actually dividing that one by 8,000, because if your derivative is too big, because remember that system is changing in the blink of an eye. This system is bouncing from 0 up at, that there's that bounce going around. Okay, so again, if we look at the trend, and I'm going to go back and I'm going to remove the set point again so we can see this ringing. You see this red peak here, that is the change. And so during these peaks, the derivative is extremely large. So if you look over here at the derivative, okay, here's your derivative. Now it's 10, 9, 8, 7. So the derivative is really, really small because it's not changing. It's not changing. But watch, when it gets ready to change, bam. Okay, it changed drastically there. It really, you can't see it. It's changing so fast because it's changing here. It's becoming several thousand. For just an instant, it's like 1,000. It's just a really, really big value, maybe several thousand. And so you don't want to add too much gain because just the change itself is going to be huge in there. So that's why my derivative, notice the derivative, I'm only at 6. Okay. And so just to kind of see what happens, I'm going to speed up the changes here, and then I'm going to increase this derivative. Okay. And okay, I changed it from 6 to 90. Now remember that 90, okay, that 90 is being divided by 8,000. Okay, so my derivative gain was 90 divided by 8,000, which is 0.01125. That's the gain of my derivative. Okay, and now you notice over here it's telling me these are not a number. Okay, the reason what's happening is it changed so fast, it went so big that the computer could not calculate the number. The number grew so big, so quick, it could not calculate it. And so it's now spitting out not a number. Okay, sometimes it's listed as NaN, not a number. And so basically I've just hosed this PLC at this point. Okay, so you see like the R5, R6, and R7 down here, they're like this -1, and then there's a number sign and an IO. They're just junk. Okay, it's not a number because the controller tried to calculate numbers that were too big for the PLC to even handle. It simply cannot handle it. And so at this point, the only thing I can do is restart my controller. Okay, because even if I come over here and I hit stop, that's what this X0 piece was supposed to do, but it's still not doing it. And so the only thing I can do is come over here, click on this, which will shut it off, and then I can turn the simulator back on. Okay. So, but that, that's just because your gain is too big. All right. So the derivative gain especially is very, very touchy. If you make that too big, especially when the system is changing so fast, it'll just blow the system up. Okay, so when you click on this, you just need to, you can use your arrow keys on your keyboard a little bit or whatever, but you just got to move it really, really slow. All right, and then come turn to my And you can see it, it's coming up here. It should hit 2500 there, WY5. Okay. And it's slowing way down now because it's getting close. And then, of course, it dropped. Okay, so have you guys figured out how to keep this trend going? This is really annoying. You got to recreate your trend every time you restart your PLC. I don't know how to get it to save. Okay, my goodness. That don't look good. Okay. System is going out of control now. You see that? That's not good. It's bouncing like mad. So I need to bring my gains down to get it back under control. Okay. So you see these tuning, as I said, the real key to this is trying to tune the controller. Okay. The code for the controller is really pretty straightforward. The key is just trying to find gains that'll give you what you want without driving the system wild. Okay, so I need to change a scaling on my trend. All right, so, but anyhow, so this is kind of what we're looking for the control. And, you know, so, you know, I have this ringing here, so, but it's not actually overshooting the final value. So even though this is bouncing around over here, it's not really considered overshoot because it hasn't overshot the final value of the process variable, right? The red is the process variable, and if I let it run long enough, okay, then it's coming up and the final value is ending up at the set point. So remember, the integrator is what is there that's going to drive the error to 0. And so let's go, I'll look at the code for this one more time. So it's basically on 2 rungs. The first rung was rung 9, which is only happening when the timer is done. Okay, and so we're calculating a new, we're moving the error and then calculating the new error. And we're setting delta t, which doesn't have to be done every scan cycle. We could have just done that in the first one or something, but by doing this, it allows me to change it if I want to. And then this value here then is calculating that the area of the trapezoid plus what it already had calculated. So this is the integration. And this is the derivative. We're just looking at the change. So the change in error divided by the change in time, which is simply delta t. Okay. And then the next rung, we're doing every scan. Okay. Now, honestly, you know, you may argue I don't have to do these every single time, but the thing is I'm scaling my analog inputs, right, to allow me to change the gains. And the thing is that if I tried to do these in a timer, then when I changed the gains, the change wouldn't take effect until the timer was done. So that's why I'm doing them every single scan. So every single scan, I'm scaling the gains for my controller, and then I'm calculating the new controller output. Now, the CO integrator down here and the CO derivative aren't changing except for when delta T is done. However, the K's could change at any time, and the error is constantly changing, right? So the error is the difference between the set point and that. So here's the error. I've actually got it displayed over here under data, right? So the error is constantly changing. So my control is constantly changing, okay? So every scan, I'm sending out a new control value. You can see it right there, right? It's updating. Every scan, it's updating. All right, so that is the PID control. Now they do have a special PID controller box here, which I've never played with it in here, but the Allen Bradley software has one too. And the key is when you start looking at those PID controllers and things, you need to understand this delta T, because they talk about delta T in those boxes, and so you need to. That's why I like to do this lab where you just do it yourself instead of using the pre-defined box, so that you understand the different terms that they're talking about inside there. Okay, but they in those PID control boxes, you can actually go in there and you can pick your delta T to be whatever it needs to be. All right, well, my delta T is whatever this timer is. So one of the things that PID box does is it gives you a different timer. Okay, so this delta T system here I'm using for my simulation of the system down below. So I just thought, well, since I already have it, I'll use that delta T for my controller also. All right, so, but hopefully you guys can get this. Did you guys get it working already, Dave or Austin or Ron? Or I guess you guys are the only ones who even bothered to log in tonight, so not yet. Okay, well, I posted that video, and it shows you this. I know you got to look closely, but that's what we're looking for it to look like. Okay, so, and this is the fast system. Okay, so I think I mean, you can copy this code, right? Basically rungs 9 and 10. At least that's where I put them. And you need to do them before the system stuff at the bottom in 11. Okay, you definitely need to do them before then. But once you get it in one of them, you can copy it and paste it to the other. So, and if you remember, I did suggest you actually start with the slow system, because this fast system is so easy to just, blow up your whole PLC like you saw me do, and then I had to stop the PLC. I had to basically reboot the entire PLC, right? So, like if we were doing this on the real PLC and it came up with that not a number, we would have to power the thing off and then back on again to reset it, because it just was hosed at that point. So you could, theoretically, I think if I had enough move statements, I put a bunch of move statements in this first scan kind of code, and I was trying to run that with the X0, but either I don't have that right or I'm missing one of them. Because if you remember, it was like setting all of these values under data. I lost my data too, but it was setting, or that's data 2. Where's data 1? I don't know. I'm still working with this software, but But the, you know, you had seen it had those not a numbers for all three of those values. I may have missed, you know, if you had some code that you could force it to go reset those back to 0, then maybe you wouldn't have to totally reboot the PLC. But you would have to have some move statements in there that would like that would force those values to return to 0. And I have some of them here under this first scan, but apparently I don't have all of them. So, but you just, like I say, you just got to watch your gains, make sure that you don't get your gains too high. So, you know, when I change them here, right, like this WX1 can go anywhere from 0 to 4095, all right, but I'm dividing it over here in rung 10, I'm dividing it by 2000, right? So it can actually only go up to a value of 2 because I'm taking 4000, dividing that by 2000. So the highest that this gain can actually go is 2. And so if you need the gain to go higher, you know, I could change this and only divide by 1000 or 1500 or something. But and then the derivative gain, I was dividing by 8000. So that WX3 goes, you know, so this derivative gain, the highest I could possibly make it would be 0.5. All right. But we had seen in the calculator, right, I currently had it at 0.01. So you just, you know, keep the derivative gain very small, or I would keep the derivative gain at 0 until you get the rest of it working. All right, so see, like this is the entire control here, but if you set those gains, if you set WX2 and WX3 to 0 and just set this, then you're just doing proportional control. So this here is proportional control only, which is what we did last week anyhow. All right, but see, the proportional control is just awful. Let me get the trend back again. Let's look at the difference. Okay, so right now I'm only doing proportional control. My steady state error is awful. Absolutely, yes. But remember, it's the your derivative is defined as being the change in the system. And so whatever your delta t is, you're dividing by the delta t because that's how fast it's changing. All right, so look at my steady state error here. I'll come back to that, Dave. But look at the steady state error. It's supposed to be way up here. It's way down here. It's just awful. All right, my error, my set point, my control value. Oops, wrong one. Okay. So it's supposed to be going up to 2,500, but it's only going to 650. I mean, the error is really bad. If I increase the gain, okay, I can, it needs to toggle again here. Give it a second. Okay. When I increase the gain, see, by just increasing the proportional gain, now it's bouncing out of control. So my gain's way too big, it's out of control. If I reduce my gain so it doesn't go out of control, then my error is still 1200. Okay, so it got smaller, but it's still bad. But now if I add some integrator, see, by adding that integrator in there, what happened? It maxed it out, I guess. Okay. Trying to get it back. Okay. I think what's happening here, you got to look at your integrator. Okay, you notice that, like right now I'm trying to control it and it's not doing anything. Look at my integrator. Remember, the integrator is adding your error up bigger and bigger and bigger. So your integrator is adding your error, and my error has gotten really huge now. Okay, my error is gigantic. And so what I need to do, if I come over here and edit this, I need to force it back to 0. So I'm going to put 0 in here, and I'm going to write this back and force my error back to 0. And now I can get my controller to work, because it just wasn't working. And that's because my integrator was just out of town. Okay, but so you got to, that's something normally in the classroom, I have you add in, like flip the switch over to the left to force your integrator back to 0 sometimes, because your integrator can get really large because you're integrating that error, and sometimes you need to force it back to 0, otherwise it's not going to work properly. But you see how, it's now driving that integrator piece. By adding the integrator piece, I'm getting my error much smaller. My steady state error is much smaller than what it was, right? Because before I was having, like, my error was 1,000. Now my error is 600 and getting smaller by the second, right? And so the error is down to 400 now, where without this integrator piece, the error wasn't getting anywhere near that. Okay. So, and if you increase it, so I've increased my proportion, my integral error there, I just increased it even more, and it looks like I've sped the system up. Okay. Okay, so by increasing that integrated gain, I'm getting it to go up way faster now. All right, the error is down to 100 right now. It's going to switch here on me real quick. All right, but the error is almost 0. It's down to 30 before it switched in. Okay. All right, so, but let me go back to Paint here for a second. And so when we have this line here, okay, so what we're doing is we are looking at a point okay, we're looking at this point here and this point here. Okay, and so for the derivative, we're looking at how fast is it changing. Okay, so the distance here, this distance is delta t. Okay, that is delta t. And, so here's my two values. So my slope is the error minus error previous divided by delta t. Okay, I mean, that's the definition of the derivative. It's the error minus error previous divided by delta t. Okay. And so, yeah, you're dividing by delta t, which is 0.005, right? So you're, even if your error was 1, right, you're dividing by 0.005. So that's going to give you what, 200? Okay. So you're getting 200 right there. And that's assuming that your error is 1. Okay. So if your error is 5, then you'd be at 1,000. Okay. So if error, well, the difference between your error, if your error minus error previous is 5, then you would be 1,000. Okay. If the error minus error previous was 50, then you're at 10,000. I can't type on a laptop keyboard here. Okay. So yeah, when you look at these values over here and you look, okay, here's my error. Okay, there's error, and then here's error previous. Okay, and they're really close. Okay, so they're most of the time, like right now, the system's real slow and they're close. But right here, for this little while I had that ringing, those values were huge. Okay, and I mean it's updating the numbers faster than it updates them on the screen, so we can't see what those values might be. Okay, I mean I'd have to like maybe go into the ladder logic and add like maybe an if statement kind of thing and say if the previous value is less than, you know, so if we came over here in our logic and let me see if I can do this here. Okay, so what I'm going to do is I'm going to put greater than so if my CO derivative, well, let's look at the error and see what it looks like first. Okay, so let's do if error is greater than error previous, then I'm going to store it in a new value. So I'm going to come over here. Let me add a value here. I'm going to call it max error. Okay, so I'm going to come over here and I really don't quite like how they do this here. I don't know which ones are being used and which ones aren't. Because they don't seem to sort them. Okay, but I think 21, 20, so I think 22. Actually, yeah, if you put it here, okay, 22 is K proportional. 24 is K derivative. So 25 is not being used. So 25, I'm going to make max error. Okay, so I'm going to make that max error, and this is going to be max CO derivative, which is going to be 26. Just so we can see these values, okay? And they're going to get huge, okay? So I'm going to copy this move statement here. All right, so if the error is, oh, I'm sorry, I did that wrong. Error, okay, so the source is going to be my error. So if my error, I'm going to move this into max error. Okay, so, but I need, in my comparison, I need that also. Okay, so this needs to be max error, not error previous. Okay, so what I'm doing is I'm just trying to show you, I'm trying to capture what is the maximum Okay, where'd that go? Okay. There we go. All right, so and then I'm going to do the same thing. This was for error. I'm going to do the same thing for my, if my CO derivative value, so this is my slope, right? This really is the slope. So if the slope is greater than the max, then the slope is going to get moved into the max. So what I'm doing is, this is just going to hold the max value. Okay, so I'm just going to find what is the maximum of these. Okay, and so then let's go ahead and accept this and simulate this again. Okay, and we'll come over here and we'll just look at those values. So we're going to look at the max error, and then we're going to look at the maximum derivative piece. All right, so the maximum derivative piece is 500,000. Okay. And max error is 2,500, which I guess the other thing now I need is a way to reset them, because that was when it first went, and the set point was 2,500 and the actual value was 0, so that was the max error. So I would I need to like reset that every once in a while maybe, but you can see that, yeah, the derivative piece is 500,000 right there. That was my maximum derivative piece, so that's huge. Okay. And that's why you can't make the derivative gains very big. You make that derivative gain too big, and then you're multiplying it times 500,000 on top of that, and you're driving the system too much. Okay. So another thing to do with the derivative, if you wanted to, would be to use a smaller delta t, right? So if you made you use a different delta t, you don't necessarily have to use the same delta t for your integrator as you use for your derivative. And so you could use a derivative piece with a larger delta t. Instead of being 5 milliseconds, make it half a second, so that you're not reacting to those really, really fast changes. Okay, but again, this system that I gave you is the fast system. This is this is a really fast system. So most of the time in manufacturing, we don't get into too many systems that are bouncing around this fast. Okay. But I wanted to show you both ends of the spectrum, and so I think I certainly did that with these two systems I gave you. Okay. All right. So any other questions or comments about that? Yeah, you definitely make a good point there. It makes a huge number, 500,000. Okay, well, if you don't, that's all I have. Like I say, the exam for next week already out there. You guys can take it whenever you want. Just take it by, I think, next Thursday was the time I put on it or whatever. But and then I'm going to be putting out the final, and that's it. Okay. So, you know, email me if you have any questions, or call me if you have to, if your internet's not working or something. But all right, so I'll leave you guys to it then.